What the fuck? It's a live stream? Okay, so here's the thing, right? I hear about Hubble constant and the expansion rate of the universe or whatever else. Now, the last time I heard about it was you did people actually have like at least original measurements, and then all this other guy comes up and says like, oh, dark matter expansion in the universe, and it's all spreading out. It's spreading out somehow faster than the speed of light at some distances. It's not. So the thing about measuring the speed of something, even though it's expanding out at the same rate as everything else, when you go out to certain distances, is that if you see one part expand and then another part in front of it expand at the same rate, right? Notice how these two fingers aren't moving very far apart, but they're moving the same rate as the rest of my fingers, right? But these two fingers went from being here to there. Does that concept grab you? Right, this is a whole half a foot away, but this is only like a couple inches. So why is it able to expand that far? Same rate. It's because of their positions. So this compared to this, same. This, same. This, same. This, whole different story. That's what's happening with the universe. It's not crazy. Right? Multiply it by a large number, then it's like boom. And you end up with numbers like it's expanding at the rate of light speed. Because the further out you go, each time that you have the expansion, you're having the same rate multiplied by a distance. But that's not really how you're supposed to. That doesn't change the pace of the expansion. The expansion is still boom, like that. It's no faster or slower than that. It's not like it's just wah. And knowing that the pace of the universe expansion is the same, it's mostly because like the person once said, an object at rest will stay at rest unless affected by something else. An object in motion will stay in motion unless affected by something else. Right? So when you get like galaxies and clusters and all of that stuff, it can hold together. But it's still, the entire thing is still drifting. A galaxy itself is still drifting through the universe. So we have initial speeds of galaxies through the universe, stuff moving around the galaxy, stuff moving in the solar system, right? The stuff that galaxies move through are moving through the universe. Because there's like superclusters and all of that, full of all sorts of galaxies. People talked about the Great Attractor, and that was some other big thing that's like, well, it's big, but it's like a supercluster big. It's not like the universe big. Or even a large portion of the universe big. The point is, that we don't have such a thing as anything out there in the universe going the speed of light. That's not what anyone has ever said. And if they have said that, they're absolutely wrong. Nothing's moving at that pace. So, when people say the expansion of the universe or the stuff that's spreading out, they gotta consider, well, okay, let's talk about something that's more recent, more local, right? Just the motion of the disk of a galaxy and how it's turning and how it's spinning and moving. And how fast can other stuff move through the universe? Each of those objects have their own speeds and rates of motion. So, really, no one thing is moving at any given constant expansion rate, as much as you might want to say it is. But even if all stuff was moving at a similar rate, it doesn't mean that the universe is applying some uniform force carrying, like, big explosion. Out in space, there's not anything else to interact with except for other nearby galaxies. So, if you're a rogue planet or a rogue solar system, or even a rogue galaxy, you're just going to go out there and you're going to keep moving at the rate that you're moving. Nothing else is going to stop you. Because, like, the only thing that can stop you, the only stuff that you'll interact with, is the electromagnetic field. Why even look for dark energy if electromagnetic field is, one, already freaking dark? You can't see it. It's everywhere. And it literally makes comets light up. But still, it's not going to slow you down. So the idea of expansion rate and this cosmic fabric of the universe that just does things, like, all of that stuff was trying to assign some underlying extra property to the universe. And it led to the idea of the Big Rip or the Big Crunch ideas, and those are all fabricated. They're all nonsense. Complete nonsense. So, the idea of the Big Rip is that because of the idea of this expansion rate of the universe spreading out, like, if you were to spread out a sheet, obviously, if you spread out so far, then everything apparently just disintegrates. Like, if you actually assume it's a spreading force for some reason, which is not what is happening. Everything's just drifting. And the Big Crunch is just the opposite of that, where the fabric of the universe spreading out so much decides to, like, rebound eventually. You have to wonder where these people, like, you realize this is an extraordinary claim to say that there is some big fabric of the universe, dark energy type stuff out there, instead of just saying, hey, the shit's drifting out that way. Wonder how fast it's going. This stuff farther away seems to be going away even faster. And it's like, yeah. The other thing about it is, how many people ever talking about the science of stuff moving away further away talk about how you gotta think about the further away you look, the longer time has taken for that light to get to us. So stuff that's 1,000 light years away, that's 1,000 years for light to get to us. So the motion that we see at this point, could be augmented by 1,000 years. And then when you got stuff millions of light years away, it could have been augmented by millions of years. And there's stuff billions of light years away, and that can be augmented by literally billions of years. Because it took that long for the light to get to us. So we got 3 different gigantic magnitudes. Like, 1,000 years is still like a large number to even concept. But you can still work on it. But the fact is that when you're looking at something, it's like, okay, it was moving maybe this fast back then. What's it doing now? We don't know. Because the light for that motion hasn't come back to us yet. So it's weird to think that people are saying that it's the expansion of the universe is like at some point light years. Because like if the expansion rate, or if the spreading out rate, which I'm just gonna call it spreading out, it's just spreading out. If the drifting is like a regular speed, right? It had its initial speed. Maybe something got flung out of a galaxy, out of its solar system really fast because it got close to a star, and that shot out really fast. Or a solar system got shot out of its galaxy, which is less likely, but it can happen. Even still, that will only have a certain speed, and it won't be light speed. We're dealing with matter here. So, the thing is that the forces that can apply to objects that end up resulting in speed are gravity assists. So, calculating gravity assists leading to extraordinary speeds, or the other idea is, of course, supernovas and hypernovas. Stars exploding or apparently black hole mergers. So we can get all these different interactions. We can talk about gigantic freaking stars exploding, or just even regular stars just hyper exploding. And the amount of force and the amount of speed that can be gained off of that, if a planet or ball, hunk of rock, or even another star, I mean, you could have another star near that in a tri-system, or a dual system, and it'll just, once the other one explodes, then it has the extra momentum of that explosion as it goes out into space. But that's about it. Again, we're dealing with rational numbers of speed. Because even the force of the explosion can only send out like small bits going fast. Bigger bits have more inertia and take more energy to go. Although, yeah, if you had a planet that was right next to a supernova and somehow that was aimed at a thing, it would get a certain amazing amount of speed, yeah. But that's like not every bit of the universe's experience, for the most part. I mean, you gotta know we're not the first series star, right? Like, according to how material is made, you start with like the hydrogen and helium and all of that, and it compresses in the star until it becomes iron. But then once you get the star's explosion, then you have all these other elements that are even more crazy, and that's only half of the stuff that we have in this planet. So you realize that in order to get the stuff that we even have on this planet, you have to have had multiple star explosions, and then what was left, the big amount of gas, coalesced into what is now the solar system with all of its stars, planets, rocks, you, me, and everything. Like, we are the grandchildren of the birth of the universe. We're not even, or great, great, great. Like, we're not the first star that showed up. Like, compared to the entire universe, our star is really young. The fun thing about that is that, like, if you think about what it takes to make the complex stuff that we have on our star, when that could have occurred, and all of that, it's another part of the Fermi paradox where the complexity of all matter, like, if you don't want to go to iron, past iron into this other stuff, like, you don't need to go past that in order to get stuff that can build life. There's all sorts of stuff that come between hydrogen and iron that can be the parts of the building blocks of life. So at what generation in the star's development are we able to start seeing life? That's a good question. But the expansion rate of the universe, it's just everything's drifting apart, drifting out, spreading, regular rate. But like the stuff at the far ends, they're moving at multiples. Okay? So if you existed at that far end versus your neighbor, you're still moving this. That's all you're doing. You're not drifting at some crazy light speed, right? But to us on this end, like, boom, we see you going away 4 times as much as our nearest neighbor going away. You know what I mean? Very simple. We see that. The pace is the same, but that's all we see. So, again, if you wanted to visit the entire universe, if you're going faster than the speed of light, or even faster than, I don't know, 100,000 meters per second is enough to visit the entire universe. It'll just take forever. But you will get everywhere. You won't just be lost eventually because stuff is moving faster than you. You don't have to go the speed of light. Not even close. 100,000 is even a high estimate. But again, 100,000 versus speed of light is literally near 300 million meters per second, and you only need 100,000 meters per second to see everything. Eventually. Because if everything's moving at, like, possibly the max is like 90,000 meters per second, then you just go 100 and you're faster than everything else out there. You don't need crazy speed. The thing is, how long do you want to wait till you see stuff that's like super far away? And we don't want to wait a lot. But I would say that humanity will definitely end up with stars that are beyond ours. Like, to get to the nearest star, it's a crazy long trip for any regular spacecraft, as max as we can try to max it out. But we'll get there. That's just the nearest star. Don't get me started on wormholes. I don't want to talk about wormholes. If, like, when people talk about wormholes, you gotta realize you're actually pinching space-time. And what a warp field bubble does is it does a bunch of tiny pinches as it goes through. Right? So imagine if you have this tiny ruler, right? And you're spreading out to the rest of the universe. Imagine all of those bits collapsing. It's still going to be that distance of it collapsed is how long it'll take for you to travel to wherever you're going. Even if you're able to expand it by, like, you know, I mean, the amount that you're supposed to be expanding in front of you is like the distance of the bubble itself. And then how fast can, like, the thing that's fascinating is that it's your space-time area that you're supposedly able to then stay inside and be able to move that entirety of where space exists forward. And for some reason they say that they haven't been able to move, like, actual objects. They've been able to move space-time or something. I heard somewhere, which is crazy. Anyway, gone through a few extra topics, but it's not super lengthy this time around. Mostly stop saying the expansion of the universe. It's not applicable. Those aren't words that we ever need to have in our vocabulary ever again. Get it out. It's just the drifting of stuff, the spreading out of stuff, attenuation. It's not expansion. There's a difference. Expansion says that there's an underlying reason for everything to just keep on spreading out. It having its own momentum isn't enough for you for some reason. But it is. And again, you're still looking, even if you're looking for an underlying material that is helping everything expand, electromagnetism is all you need for that. That's the underlying material that is everywhere. So what would you, like, if you have electromagnetism, people downgrade it all the time, but it literally is the stuff that's making lightning storms and the electromagnetic field around the goddamn planet and coronal mass ejections. This shit's big. That's electromagnetism. It's not like the sun. What is it? Solar flares. That's the word. Solar flares are literally just electromagnetism saying, yeet. That is a magnet going, poof, and a bit of the sun is just being flung out. And it's freaking huge. One solar solar flare can be as wide as multiple Earths, for crying out loud. Why do you think electromagnetism is not powerful? Is not huge, is not everywhere? So then if you think about it, and if you think about light being energy that has traveled everywhere because of electromagnetism, then you have to understand that, I mean, there was one point when I thought about, oh god, don't get me started on quantum entanglement. Quantum entanglement is like a golf ball going through the air and all of its constituent parts are going through at the same rate. And so its spin, everything else that has to do with it, as long as it's not going super fast, that golf ball is going to basically stay intact. Quantum entanglement says that you can have stuff that's like super fast and super far away, or it doesn't even have to be going apparently fast. It's just super far away, and it has that same connection of like its momentum and its speed and its relative whatever. Quantum entanglement says that you can have these connections like super far away. They put it in a goddamn book and they say a Nobel Prize for it, but it hasn't been proven. Quantum entanglement apparently does not happen. No, it doesn't. All they proved in that experiment where they shed some light on a specific atomic structure, I think it was calcium, is that they shone the light at that molecule, right? It's split into two equal halves, and all we said on either side is that the two equal halves, yeah, they're opposites of each other and they are correlated. It's like splitting a baseball in half and saying the one side is the same as the other side. Yeah, that doesn't prove entanglement. That just proves that you have both halves of the ball. If you think of a photon as possibly being both halves of the ball, the other thing is, if you're talking about photons, is it not also true that instead of splitting a photon was sent one way, hits something, and in two different directions that something then emits light? And it's a specific molecule, specific atom that achieves that the light is emitted in both directions. Why the hell would you be able to then grab that light as it's by the way, light going the speed of light freaking fast? You're supposed to be able to grab that somehow, which, yeah, you can do that in a Bose-Einstein condensate apparently. This is true. Right, so you got these globs of like electromagnetic controlled little bits of matter, and a photon can just be stuck in there. Nutty. They're using the same type of technology as like sound, being able to control the vibration, the motion of air through in a pocket of space, directly in the path of the thing that's moving. Like, it doesn't matter if it's sound, it's whatever vibrations, but instead of using vibrations of sound, they're using electromagnetism, and the electromagnetism then makes it so that you have this pocket of material that does not move. So it's super cold because it's super still. If you think of hot and cold being either fast, which is hot, and slow being cold, which is how it is. So they slow it down, turns cold, and you can get a light, photon of light be stuck in there. So let's say you have these quantum entangled bits of light, right, in a little packet, and you somehow are able to make it so that there's Bose-Einstein condensate is constantly maintained, which this is a big thing. It's the size of a standard fume hood, right? Or it's the size of that giant hydraulic press box that they use. Like they use a big box around the hydraulic press so it doesn't or if you know how big a fume hood is, or a big fish tank, large fish tank. It's like this machine is massive. It's not just something you can easily be portable at the moment, but you should be able to miniaturize it so that you could have Bose-Einstein condensate inside of a watch if you were clever enough. They're not, but we're getting there. The point is that if you have this box, it has the Bose-Einstein condensate in it, so it's super vibrated to the point, or it's super controlled so that it does not move. Gets really cold, shine the light into it, have it stuck there, then, beyond the electromagnetic stuff that you're doing to make it cold, do something else to affect the light. And you're supposed to be able to expect the outer light that you have, wherever it is, to be affected. No one's done that and achieved anything. First of all, that experiment has never taken place. Ever. It has not taken place. Second of all, it wouldn't work even if they did. And in the case, obviously, I'm going to say this, in the case if it did work, then they say, well, you can't transmit information this way. You're kidding me, right? If you have a grid of these, all it takes is for you to make, like, technically the smallest amount you need is like 3. Then you simply interact with the 2 of them, and the 1 stays off, and you have a line that you just drew somewhere else. Right? If you have a big grid, you can start drawing weird designs and make a QR code if you wanted to. If you wanted to, you could make an entire display. And the best part is, if entanglement was real, these entangled particles, it should not matter. Once you touch them, they should still have the entanglement property, because there's no reason they shouldn't. There's no reason. Because, like any other part of the golf ball, as it goes through the air, there are some parts that are hitting the air straight on. There are some parts that are at the top of the golf ball that are hitting across the top with air differently at different angles that become narrower, narrower, narrower until you get to the top of the golf ball and it's like just screaming across. You got parts on the back of the golf ball that are at some times not affected by air whatsoever, but then because of the fact that golf balls usually spin as they travel through the air. They will be affected by air, and they didn't stop being a golf ball, right? Golf ball, tennis ball, whatever, baseball. So you move at certain speeds. Start moving at relativistic speeds, and you end up with stuff like if you still are able to cohesively interact with each other, because you started off as one thing, right? There's a certain point where all of that stuff and all those connective bits on the electromagnetic spectrum and all that can only have so much influence. But Einstein obviously did not believe in quantum entanglement because he didn't believe in all of that stuff. He said there had to be hidden factors. The hidden factors are, and it's very simple, that if you split something down the middle, the one side's going to see the one half of what you split, and the other side's going to see the other half of what you split. That's all there is. Which means there was a structure that if it happens that way, then it means that you had this tiny little object, a photon, has structure. It's not a fine, one-dimensional basic point of electromagnetism. After all, then it is actually a physical object with a certain amount of diameter, specific properties inside of it that make it do the thing that it do, instead of just being electromagnetic wobble. Like, it can move with wobble frequency or something, but like, I don't know. That's the thing. But to get back to the expansion rate of the universe, it's still just this. How do I justify making videos this long? Neil deGrasse Tyson does the same thing. What are you talking about? Of course, they talk about multiple different topics. Wait, that's what I'm doing. No difference. Just if you have science to talk about, usually your brain will think about other sciencey things, like how when you have let's say you have an object that's on a boat with a certain amount of weight, and this really bothered me. Okay? There was a science talk talking about how the amount of water that you displace when you're in a boat versus when you yourself are in the water is the same. And I can't help but think that that is completely not true. Because the amount of water that I displace while I'm in the boat is dependent on my weight on the boat and its displacement factor. So if I'm on a boat, that it's like depending on, okay, let's say it's a simple thing and you have a basic like U-shaped boat, so it's like a cup, right? And it's that usual like fishing boat thing or canoe or whatever you want, right? The statement was by Physics Girl, and it's wrong, by the way, that the amount of water that you displace while you're in a boat will be the same as once you're in the water. Well, if you do that with an anchor, the anchor does not displace a lot of water while it's in the water, but it pushes that boat down and displaces a bit more. But let's say that you have something very simple example. Let's say you have a sandbag and balloons, right? The amount of weight that you displace while you're in the boat is based off your weight. So if you take that sandbag and balloon and you put it into the water, the sandbag will hold the balloon down and the balloon will displace the water, as long as it doesn't change under the water's pressure. Say you got one of those beach ball balloons. It's not gonna just compress. It'll stay basically the same size as you put it in the water. So the sandbag holds the balloon down, and you know that that balloon has a certain volume, and that's how much water the balloon is going to displace. Same experiment, deflate the balloon, but put all the air into a capsule. That capsule has nowhere near the same volume as the balloon did, right? Like compared to an entire beach ball that is multiple feet in diameter, let's say it's 2 feet in diameter, and a capsule that's a centimeter big, yeah, that capsule's not going to do crap to the water. It's going to do its surface area of displacement, and the thing is, it holds the same amount of air, but it's just really compressed. Let's say you have a capsule that's able to do that. Alright? That basic example, or any amount of compression. Let's say you just compress it 2 times pressure. Well, now, that inverse square law, you understand that the volume just decreased by half. The entire area has decreased let me get this right. But you kind of understand it. Square cube law, that's what I meant to say. Not the inverse square law, the square cube law. Yeah, if you half the height of the square, right? That versus a cube, you've taken it down by 1/8. Which is nutty. So you're now displacing 1/8 of the amount, but you've compressed the air to be half of the, or to be double the pressure. So it's taking up less space. It's pushing away less water. It's the same amount of air. It weighs the same, but it's just compressed. So you're still going to weigh down everything the same amount, but now you don't displace as much water. And that's the problem. And I don't know why. I don't know why Physics Girl made that mistake back when she made it. And I made a video talking about it. People didn't like that I said that. And they thought maybe I was disrespecting her or something. Well, it's like any scientist is able to say, hey, I've made a mistake before. I made the mistake of saying that an electron would go 2.2 quadrillion atomic widths, and if an atomic width is 1/10 of a nanometer, it would actually go 22 quadrillion atomic widths per second, because 2.2 thousand kilometers, or 2.2 million meters per second, correct way to say it. It's actually a lot faster to say. Well, I don't know. Million meters, 1,000 kilometers. Well, you gotta just. Well, kilometer is a two-part word, so you got meter. Million seems like one. It's a long word, but it seems like one word, you know? Million. Boom. Done. It's as fast as saying boom, million. Somehow kilometer is just as long of a word, but it feels like two words, like race car. A race car is even shorter, and that's two words. The point is, talking about 22 quadrillion atomic widths per second is more accurate to the size of the electron and the area that it inhabits versus saying kilometers, because kilometers has nothing to do with the size of an electron. Electrons are very extreme tiny, right? They say 10 to the minus 18th is an electron. I just refer to the 10 to the 10th because of atomic. The atom's size relates to the electron's orbit. That's important. That's the factor that I'm focusing on, because when you think of I should have done the proper translation for the amount of the orbit, because once you have that figured out, I probably don't need to eat all these pancakes. Once you have the orbit size figured out, that divided into the total length that it's going, then you end up with, like, if it's 22 quadrillion atomic widths per second, then it's about 5 quadrillion orbits per second. So for every orbit that an electron does, it's like a spool of yarn, and I've talked about this in another video. Every orbit that an electron does, it'll meet itself when it comes back around, because it's already happened so fast. So it has to move over to the side a little bit. take up another different bit of space. But because it's doing that so many times, quadrillions of orbits, like just imagine hundreds, and it's like a ball of yarn going around and around and around and around. You're going to end up with many layers of string. So the thing about an electron going around an atom is like wrapping string around a baseball. The string is very small and the baseball is huge, but once you get all that string around the baseball, you still end up with a large cluster of string around that baseball. That's what happens when you take an atomic electron-sized little particle, multiply it by 5 quadrillion or something. Imagine all of those around that atom, right? And then twice as many when you have bigger atoms. Like we're just talking about hydrogen here. You get to carbon or whatever, and you end up with 6 electrons going around it. So or is it 8? You end up with all these bits that are going around it, and they all have individual bits of connectivity. Anyway, well, we're talking about the spreading of the universe. Yeah, spreading. Stop saying expanding, please. But yeah, the simple example of a sandbag and a balloon versus a sandbag and compressed air means that, yeah, if you have different compressions of stuff, then the weight that you push down on the boat and the displacement of the water that you have for that is simple, but then it changes whether you're totally expanded or if you're totally shrunk. Now, if you take that same balloon and you put hot air into it, that expands the amount of air. If the balloon is allowed to stretch, then it'll be even bigger and it'll displace more water, as long as the water doesn't stop it from being hot to expand. So the idea of that hot air balloon in more water, it's like you're going to expand it and you're going to have even more displacement. It's big. So, yeah, this is stuff that a submarine would have to understand, because that's how you're able to have the air compression and water be pushed out of the ballast and all of that, and you'll end up raising and falling depending on just how your air is either in the tanks or taking up a large space in the ballast. And that's a simple thing. But I don't understand how anyone can get that false. But it's these edge cases of like, is the balloon expanded? Is all of these other things? That's like, but that's a simple idea, and it should be that it's easy to track. It's easy to think of these edge cases for stuff. But there's a lot of edge cases that scientists just maybe don't think of because they already have a lot of other stuff in their head. Like I've got a bunch of stuff in my head. There's all sorts of stuff that I can expose myself to and learn. And there's only so much that I can actually like I can keep a lot of it in my head, but I can only remember so much of it. So that's why you gotta keep on refreshing your brain. Keep on learning new things. That's why this live stream sponsored. It's not brilliant. Um, I haven't used Brilliant yet. Haven't even tried. Been watching people play Peak too much.